the last lesson, we looked at two rules of probability. The first rule states that the probability of any sample space is always 1. So, the probability of all the events in the sample space comes to a total of 1. The second rule is that the probability of something not happening can be calculated by subtracting the probability that it will happen from 1. These two events, that something will happen or something will not happen, are called complementary events. Today, we want to work out rules for the probability of completely separate event spaces in the sample space. For example, throwing a 6 on the dice cannot happen at the same time as throwing a 5 on the same dice. These two events belong in separate event spaces or subsets of the sample space. We call them mutually exclusive events. We also consider events that have some overlap or intersection with each other. We call these inclusive events. By the end of this lesson, you should be able to work out probability statements for mutually exclusive events and also for inclusive events. We're going to use a story to help us understand exclusive and inclusive events. This story is called the Inaza's Enigma. An enigma is a riddle, a puzzle, or a mystery, and Inaza's is a tricksy creature that terrifies its victims with, no, not sharp teeth. Let's listen to the story.
Deep underground lived the Inazas, a creature known for its habit of setting traps to trick unsuspecting victims into living with it underground. The Inazas was a very playful being, so its traps took the form of a puzzle or a riddle to solve. Now the Inazas kept watch over the only river in the area, so the people and animals that lived there had no choice but to risk an encounter with the Inazas when they needed water. The people of the village knew it was dangerous to play the game of the Inazas, and so they had one sacred rule. Never play the game if the Inazas has a greater chance of winning than you. On a fine sunny day, Trabora brought his father's cattle to the river to drink as usual. Although he visited the river often, Trabora had not yet been approached by the Inazas. But on this day, the Inazas hovered over the river, watching him approach. Trabora went bravely forward and asked the Inazas to let his cattle drink from the river.
Of course,
chortled the Inazas.
But you know the rules. You must play with me for first. This game is for fun. It's easy too,
cried the Inazas gleefully.
See here, I have a basket full of colorful eggs.
Trabora tried to look inside the basket, but the Inazas pulled it back smartly so he couldn't see inside.
Naughty, naughty! No looking, no peeking, no cheating, no sneaking!
Laughed the Inazas.
Come, friend, it's too easy. All you must do is reach in and pull out an egg without looking. But now listen closely to what I tell you. Yellow eggs there are, a quarter to be precise. Blue eggs too, 10%, quite nice. Then red I see, 0,2 if you please. And green, so green, 2/5 there are of these. Purple is next, last and yes, the least. 0,05. You see what I mean by the least? Yellow eggs there are, a quarter to be precise. Blue eggs too, 10%, quite nice. Then red I see, 0,2 if you please. And green, so green, 2/5 there are of these. Purple is next, last and yes, the least. 0,05. You see what I mean by the least? Now you can take your chances. I'll give you 2 ways to win my game. For first, if you choose an egg which is red or green, then you win, and you can use the river for free. But if you choose an egg that is yellow, blue, or purple, I win. But maybe you don't like those chances. Your kind is always complaining about the chances in my game. So here's a second way to play my game. If you choose an egg that is blue, red, or purple, you win. If you choose an egg that is yellow or green, then I win. So which is it to be? Come on, don't be shy. To choose your odds and let's play, or from thirst, you might die.
Now Trabore's cattle were thirsty and there was no other water for many sons' walk, so he was forced to play. But he had the village rule ringing in his ears. Never play the game if the Enazas has a greater chance of winning than you.
Which option would you choose? What must Trabore choose to make sure he wins? Let's see what Refilwe and Gerard did to work out Trabore's options.
There are 5 colors, and I think there are 5 possible outcomes: red, green, yellow, blue, and purple. And in the first option, Trabore wins if he chooses one of 2 of the 5 colors. And in the second option, he wins if he chooses one of 3 of 5 colors. I reckon there is more chance of getting one of 3 colors than of 2.
Hold on. There has to be more than 5 possible outcomes to think about. Although we don't know how many eggs there are altogether, but there can't be just one of each color.
But we do know what percentage or what fraction there is of each color. There are definitely more of some colors than others.
So some colors have a higher chance than others of being picked. I nearly fell into a trap there. But if we don't know how many eggs there actually are, how can we know the total number of possible outcomes?
We can work out which of these fractions is the biggest. The problem is, the Enazas has given us all the amounts in different forms.
We'll have to convert them all to one form. Let's convert them all to proper fractions, because I find those easier to work with.
Okay, I get 1/4, 1/10, 2/10, 2/5, and 5/100, which is 1/20.
If we make them all 20ths, we get 5 20ths, 2 out of 20, 4 out of 20, 8 out of 20, and 1 out of 20. And if we add these up, we should get 20 20ths. 5, 7, 11,
19, 20. Excellent. They add up to 20 20ths, which is 1 whole.
Look what we've got now. There are 8 green eggs for every purple egg.
But we still don't know how many eggs there are altogether. It could be 20, it could be 100, or it could be thousands.
You're right. But we do know that for every 20 eggs, only 1 of them is purple, but 8 of them are green. So we don't need to know how many eggs there are altogether.
That's true. So let's work out the chances of winning with each option that Trabore was given.
Can consider a case where there are 20 eggs. That way, the possible outcome is exactly 20. In choice 1, Trabore wins if he chooses a red or a green egg. And out of 20 eggs, 4 are red, 8 are green. So if he chooses any of those 12 eggs, then he has won. There's 12 favorable outcomes.
But if he chooses a yellow, blue, or purple egg, then he's lost.
There are 5 yellow, 2 blue, 1 purple. That means there are 8 outcomes which aren't favorable.
So this option gives Trabore a good chance of winning. He has 12 chances out of the 20 eggs of choosing a winning color. Now let's look at the second option.
Okay, if he chooses blue, red, or purple, he wins. So for every 20 eggs, there are 2 which are blue, 4 red, and 1 purple. Wow, that's only 7 favorable outcomes out of 20.
That means that there are 13 favorable outcomes for the Inazas. Hey Trouble, definitely don't take this option.
Remember, all we've done is see that Trabor has more chance of winning if he chooses the second way of playing the game. His chances are higher, but he could still pick one of the 8 losing egg colors. That was fun. Now, let's see how we can use probability language and Venn diagrams to represent the possibilities from this game. In the first option, we wanted to know the probability of Trabor choosing either a red or a green egg. This would be written as P and in brackets red or green. The word or is very important here. Only one egg will be chosen, but there are 2 favorable outcomes, red or green. If we represent this with a Venn diagram, there are 5 subsets of possible outcomes. The sets of red, green, yellow, blue, and purple eggs. The red and green sets together make up the favorable outcomes for Trabor. The probability of choosing a red egg is 4/20. The probability of choosing a green egg is 8/20. So out of 20 eggs, 12 are favorable. In other words, we add the probabilities of both events. So we can work out the probability of choosing a red egg or a green egg. It's the probability of choosing a red egg added to the probability of choosing a green egg. This gives us 12/20. When working out the probability of one event or another event happening, the rule is add the probabilities of the 2 events. Let's look at another example from the story. Let's play our choice 2 again, this time choosing a different color. What was the probability of choosing a blue, a red, or a purple egg? The probability of choosing a blue, a red, or a purple egg is the probability of choosing blue plus the probability of choosing red plus the probability of choosing purple. So this becomes 2/20 plus 4/20 plus 1/20, which is a total of 7/20. This was Trabor's chance of winning in choice 2. The complementary event to this would be Inaza's winning, and we can write this as 1 minus 7/20, which is 13/20. Let's hope that Trabor made the choice that gives him a 12 out of 20 chance of winning against Nazas. His cattle must be very thirsty by now. In this story, each egg is only one color, so it's impossible to choose an egg that is both red and green. In other words, on the Venn diagram, each of these sets is completely separate from the others. No eggs are in more than one subset of the sample space. Events that are separate like this are called mutually exclusive events. Either the one can occur or the other, but never both. Either Trabor can choose red or he can choose green, but he can never choose an egg that is both red and green. But there are times when event spaces can overlap or intersect. We saw that in a previous lesson with hula hoops and the beanbag. The beanbag can belong in 2 event spaces. Here's another example. Suppose the Inazas gives Trabor a new puzzle, this time using a dice. He says that Trabor wins if he throws an even number, but it has to also be a number less than 5. What chance does Trabor have of winning? Let's represent the problem with the Venn diagram. First, let's represent the sample space for the throws of a dice with a rectangle. Then, we need a set of even numbers that are possible on a dice. That's 2, 4, and 6. We also need a set of numbers less than 5 that are possible on a dice. That's 1, 2, 3, and 4. Look at the 2 event spaces. The 2 and the 4 belong to both event spaces, but there is only 1 2 and 1 4 on the dice. We can't have 2 and 4 represented twice each in the possible outcomes because the dice only has 1 2 and 1 4. So the event spaces need to overlap or intersect like this. These are called inclusive events. A number less than 5 can also be an even number, so the sets are not mutually exclusive. A number can appear in both subsets. Now, what is the probability of a number thrown being either an even number or a number less than 5? Let's see what happens if we just add the two probabilities together. The probability of throwing an even number is 3 out of 6. There are 3 favorable outcomes out of a sample space of 6. And the probability of throwing a number less than 5 is 4/6, because there are 4 favorable outcomes out of the 6 possible ones on the dice. Now, if I add 3/6 and 4/6 together, I get 7/6. Oops, 7/6, as you know, isn't possible. We can't have a probability larger than the total number of possible outcomes. So what went wrong? A throw of 2 and a throw of 4 were counted twice. They were part of the 3/6 counted in this subset and part of the 4/6 counted in this subset. We need to subtract the numbers in the intersection of the two sets, and we would get 3 numbers in this set and 4 numbers in this set. This makes 7 numbers. Then we subtract the 2 numbers in the intersection of the 2 sets to get 5. So the probability of getting a number that's even or a number less than 5 is 5 out of 6 numbers. What happens to the other 1/6 chance then? Well, neither of these sets includes the number 5. 5 is still in the sample space, and there's a 1 out of 6 chance of throwing a 5. Now let's look at the probability language for this. The probability of getting a number which is even or less than 5 equals the probability of an even number plus the probability of a number less than 5 minus the probability of a number which is even and less than 5. So putting the numbers in, that's 3/6 plus 4/6 minus 2/6. There are 2 numbers which are both even and less than 5 out of the sample space of 6, and that's 5/6. This is an important rule of probability for inclusive events or events that intersect with each other. Using A and B to represent the events, we can write the rule as: the probability of event A or B occurring is equal to the probability of A plus the probability of B minus the probability of A and B. Compare this to the rule we found for mutually exclusive events. In a case like this, where we know that the 2 events don't intersect and are completely separate from each other, we don't need to subtract the probability of A and B because there are no events common to A and B. So, if you are asked to work out the probability of one or the other of 2 events occurring, first decide whether the events are mutually exclusive, that is, they cannot both occur at the same time, or whether the events are inclusive, that is, something can belong to both of the event spaces. If they are mutually exclusive, add their probabilities. If they are inclusive, then add their probabilities and subtract the probability of the outcome belonging to both events. Well, we worked out which choice gave Chabor a better chance of winning his game with the Anazas. Now it's your turn. Here's another tricky game of chance from the Anazas. This time, there are only 3 different colors of eggs: yellow, blue, and red. 1/5 of the eggs are yellow, 50% are blue, 6/20 are red, and half of the eggs of each color are striped. If you choose an egg that is yellow or striped, you win. If you choose anything else, the Anazas wins. What are your chances of winning? Write down your chances as a probability statement. Well, that's all we have time for today. Also, it brings us to the end of our series on probability. But today's episode wouldn't be complete if we didn't finish the story about Chabor and the Anazas. So let's go back and find out what happened when Chabor finally gets round to choosing an egg.
For a long time, Chabor sat around thinking about the village rule that says, never play the game if the Anazas had a greater chance of winning than you. And his cattle were getting more and more thirsty. Suddenly, the Anazas called out from the cloud.
Hurry up! Which way do you want to play the game?
But Chabor had been smart. He'd used mathematics to work out which way would give him the best chance of winning.
I choose the first way.
And he put his hand in the basket. Trabora had beaten the Inazis, and from that day on, he was able to take his kettle to the waterhole without ever seeing the Inazis again.